Assalamu alaikum dear students. Welcome to Thin Film Technology course, lecture number 16. We are having a discussions on thin film depositions. So we will continue the discussions in this section as well. But here we will have an introductions to evaporations. It's another techniques for thin film depositions. In this sections we will have some brief introductions to evaporations, and then in the next section, that is in the coming lectures, we will discuss different types of the evaporations. So let's first proceed towards these sections, that is evaporations. So before going into details of the evaporations, let's first discuss some things, the basic types in which we included the evaporations, or from which we have the evaporations. So you know that we have a techniques. At the start of the thin film depositions, we said that we have two main techniques. The first we call chemical vapor depositions, and which normally the chemical reaction that been involved for the deposition of thin film. And then we say that the second main techniques that we have for thin film depositions, which do not involve chemical reactions, and we call that a physical vapor depositions technique. So the evaporation is basically one of the type of the physical vapor depositions techniques. And here we say that in physical vapor depositions we have two basic types of the reactions. That is, we have evaporations and sputtering. That evaporation and sputtering are the two basic kinds of the physical vapor deposition techniques. And we remember that evaporations and sputterings, they are further be divided into different types that we will discuss later on. So we remember in PVD, or physical vapor depositions, chemical reactions are not involved. All the process that occur here is basically the physical reactions. So sometime if we have some sort of the chemical reactions, so that should be only for reactive evaporation or reactive sputter depositions. And you know that this kind of reaction is not widely utilized. So normally we do not have chemical reactions and PVD. So when we say that, just like we discussed earlier, that physical vapor deposition has two basic types, that is evaporations and sputtering. So let's first come towards the evaporations. In evaporations techniques, basically we utilize the material source, and those are that material source is heated to a high temperatures and a vacuums. The heating is generally performed either by the thermal, by some thermal techniques. That in that particular technique we directly utilize some heating source by applying the voltage, or the heating can be performed by electron beam method. That is, we do the heating by electron beam evaporations. We utilize the electron to heat the source materials, and that we call e-beam methods, or electron beam evaporations. So in these matters, in evaporations, the materials is vapor transported to the target, and vacuums. Film quality is often not as good as sputter film. You know that we have two types of the physical vapor depositions, that is evaporation and sputtering. And here we are saying that we can deposit thin film, and the thin film quality is very good. But when we compare that quality to the other type of the PVD, that we call sputter depositions or sputtering, so the film quality that we grow via evaporation is not as good as we do via sputtering techniques. And we remember the sputtering techniques normally involves energetic bombardment of ions to the ash deposit film, which make the film denser. And we remember the film techniques and the evaporation techniques can be monitored precisely by using a quartz balance. This is something, a good characteristic of the evaporation technique, and which we can monitor the film thickness. So this is necessary. Why this is necessary? Because the depositions is not reproducible. Once you deposit the thin film, so you cannot, do the reproducibility What it mean? It mean that we have tiny change. A tiny change in the temperature lead to a large change of the deposition rate. When you're running the evaporations system for the deposition of the thin film, and you just have a smaller increase in the temperature, so that smaller increase in temperature is responsible for a huge change or a large change in the deposition rate. So what we should do, that's why we are saying that temperature is not monitored but power is monitored. So you have to utilize that, you have to control the temperatures via the power. The temperature is limited here is the with the help of the power. So you better to make sure that how you control, or you should be expert in how to control the temperatures via controlling the power. Sputter depositions, we also have with sputter deposition, we also have sputter etching. So what actually we have or we do in sputter depositions, in sputter depositions we normally have the material that is moved from the target by momentum transfers due to the collisions by due to the collisions by the ion. We will discuss that later on with full details that what actually happened in the sputter depositions. So gas molecules are ionized in a glow discharge, that is plasma. Strike the target and remove mainly neutrals atoms. So sputter atom condenses on the substrate. This is something very short for the sputter depositions or sputtering process. Just something like you can call it as definitions for the sputtering. The detailed discussions we will have later on in the coming lectures when we will discuss the sputter deposition process and its different types. So for now, you just should have some these short definitions are short differentiations for evaporations and for sputterings. And we remember in sputterings, it's not 100%, we can say it's not 100% in vacuum. Basically we utilize gases like argons, and the pressures ranges from 5 to 50 millitars. We utilize argon gas, and you know that the argons ion, they're basically utilized for the sputtering process. That has been utilized to sputter the targets, and those sputter atoms, they are being moved to the substrate where they have been deposited in the form of thin film. So that's why we're saying that this is not a vacuum. Why? Because we utilize the gas or the ions for the sputtering process. So let's first come toward the evaporations, and the evaporations process, since it's all occur in the vacuum, so it can also be called as a vacuum depositions. All the process occur in high vacuum. So as a result, this process of evaporation is also called a vacuum deposition. So it's the typical experimental setup. That is, we have a huge chamber. In this chamber, inside we have the heating source. It's basically a resistive heating or the e-beam heatings. Uh, Above this heating source, we have here the source materials. So what actually happened, what is happening, that we will discuss in the coming slides, on the or in the coming points. So here you say that this is the chamber, the whole chamber is evacuated to a high vacuums. And here you know that we have the vapor holders, and this vapor holder basically hold the vapors. We have the atomic clocks when we start the process. During the process, we have the atomic clocks from the source materials that is being moved toward the vapors, where they deposit in the form of the thin film. And here we have, you can see it here, we have the vacuum system that's been opened toward the exhaust. That is responsible for creating the vacuum and the chamber of the evaporation system. So now let's come towards the evaporations, it's more formal discussions of the evaporations depositions. So in evaporations, source material is heated in high vacuum chamber. The pressures that we maintain are the pressure which is necessary for the evaporation is smaller than 10 raised to power minus 5 torrs. Just because of that, it's been named as vacuum deposition. I mean, since all the process they are being performed in this chamber at high temperatures, sorry, it's high vacuum. So just because of that, we can call the process, the evaporation process, as the vacuum depositions. So what it mean? It mean that during the depositions, high vacuum is required. And what it mean, why we required high vacuum? We required high vacuum to minimize the collision of the source atoms with the background species, that is light up size depositions. So just like we discussed previously, here you can see that we have a heaters or the heating source, and we remember the heating is done, I mean, we already mentioned here, the heating is done mostly by resistives or EV beam source. So surface interactions are physical, I mean, we don't have any chemical reactions here. So as a result, it can be very fast. How much fast? I mean, it should be greater than 1 micrometer per minute, I mean, is the possibility. But be remember, film quality may suffer. I mean, the reaction process is very fast. I mean, it can be a merit of this kind of reactions on one side, but in another side it can be a demerit because it can also affect the film quality. So for R&D typically we have 0.1 to 1 nanometers per second. So in these techniques we have a high stacking coefficients at low temperatures, that is its atoms stay where whenever it heads with the limited surface migrations. So all these processes leading to poor conformal coverage are significant shadows. But this also makes evaporation the most popular thin film depositions for nano fabrications using the laptop process. Deposition rate, we remember deposition rate is determined by emitted flux and geometry of the source and the vapors. And similarly, evaporation is not, be remembered that evaporation is not widely utilized by the industry as compared to this. Sputter deposition is mostly employed or utilized by the industry. For microfabrications R&D, evaporation is an important. Evaporation is as important as sputter depositions. So in evaporation, we say that one of the concept that we utilize that of man free path, and we say it's very important for the film thin film depositions that we call vacuum pressures and man free path. So here you can see it in the and the figures that how we draw the relations for the main free path, and it's how I mean so how we can calculate the relations for the vacuum for by utilizing the concept of this main free path. So let's have I mean some let's draw some basic relations. That's how the main free path affect the vacuum for the depositions of the thin film where the evaporation. So let's assume, I mean, here you can see that we have particles, we have a source. From this source we have particles that move with the velocity v, with the speed v towards the vapor. So we assume the particles of diameters, we say that this is the particle diameter, that is equal to sigma, moving with the speed v, and it has a collision cross sections, and the collision cross sections is equal to pi sigma square. So the collision volume swept during the time that we denoted, I mean a small amount of time, a fraction amount of time, that is dt is equal to pi sigma square v dt. So the number of collisions during dt is equal to n by v, n to pi sigma square v dt. We remember here in this particular relations, n over v basically mean the number density. I mean n by v normally means the number density. So the average free path that we denoted by lambda is equal to v dt divided by the number of the collisions. So which in turn we can write n over v into pi sigma square whole raised to power minus 1. In more rigorous treatments, you know that we have a relations pressures volume pressure time the volume is equal to n kt, so most general relations. So by utilizing these relations, we get the values for the lambda is equal to n over v pi sigma square under root 2 whole raised to power minus 1, which is equal to kt divided by under root 2 pi sigma squares into phi. So if we assume S is equal to 3 angstrom at the temperature is equal to 300 Kelvin, so we should have pressure time, the main free path is equal to 7 and 2 7.8 and 10 raised to power minus 3. And we remember when we have the unit of pressure, the unit different units for the pressure, and which 1 torr is equal to 1 millimeter of mercury, which is equal to 1 over 760 atmosphere. So what it means, it means that if we have a free path lambda equal to 30 centimeter, so then a pressure equal, then a pressure smaller than 2.6 into 10 raised to power minus 4 torr is required. I mean that is I mean here you can see that we have a relations between the pressures and the main free path, and we say that when you multiply both of them, so it's equal to this particular number. So here if you put the values, I mean you put the values for the lambda, and you say that lambda is equal to 30 centimeter. So we have pressures that is smaller than 2.6 10 raised to power minus 4 torr, I mean is required for the film depositions. And you know that the typical vacuum for the evaporation is smaller than 5 and 10 raised to power minus 6 torr. So the you know that many gases I mean that being utilized I mean it's as reactions in the depositions techniques. I mean for the deposition of film or thin films, we can have varied gases. So the main free path of various gases are, I mean here you can see that we have different gases, that is oxygen, nitrogen, hydrogen, helium, argon, neon, xenon, carbon dioxide, water vapors, chlorines, and ammonia. So here you can see that we have the main free path, and the main free path at low pressure at 20 degrees centigrade. Here you can see that these are the main means the low pressures uh, at 20 degrees centigrade. And here we have drawn relations, I mean the pressures we have converted into a length scale, and that is here you can see that we have atmospheric pressures which is equal to 760 torr, and if we convert that into a length scale, so we say that it corresponds to 40 nanometer. So what it mean that is smaller than most Jeff features. And if we come from atmospheric pressure to low vacuum, so low vacuum it means 0.76 torr, which corresponds to 40 micrometers, which equal to, I mean which mean that larger than most Jeff features. But if we have medium vacuum, so medium vacuum mean 7.6 millitorrs, which corresponds to approximately 4 millimeters, which is larger than working gap. If we have a high vacuum, so you know that high vacuums correspond to 7.6 microtorr, which is equal to approximately 4 meters, that is larger than the chamber. So what it mean that evaporated materials travel straight to vapor, line of straight, thus is very directional. So mean that evaporation process is a very much directional process. Here we have the photographs of different materials that can be utilized for the evaporation. So here you can see that We can utilize the material, the source material in the form of the grains. We can utilize this like in sugar palm. You can utilize in a small powder. You can utilize, I mean, in powders. You can utilize like salt rock forms. And similar again, when you can utilize that in the tablet form. I mean, here you can see that is this structure, and this structure is most look like some sort of the phthalate. I mean, these are the different type of the source material. I mean, it's how we can utilize the source materials when normally we perform the evaporation process. So that's all we have. I mean, journal introductions for the PVD, and particularly for um, evaporations. Thanks for watching. See you in next lectures with more detail about evaporations. Till then, bye bye.